Okay, so let's take a look at what we've got going on this week. Jay kind of screwed up and forgot that when he made his homework, he made reactions for both regular carbon-carbon double and triple bonds and then those aromatic compounds on the same sheet. So you really couldn't finish that homework, and I hope most of you realized that and stopped before you got frustrated. And because I decided when we were lecturing that we'd try to divide up the naming instead of covering it all in one big day. And so, I forgot to change the homeworks to reflect what we had changed in class, which, that was a last minute decision. So we'll say that homework, since we're going to cover it today, is due Wednesday. And then we're going to cover naming of aromatics and reactions of aromatics today. And that was 20C. So 20B and 20C will be due on Wednesday. So if we're looking at this week, Tuesday, Wednesday, Thursday, Friday, we've got lab, 21 due? Or is it 20 or whatever? The one on alkanes. So do I. And then we'll have 20 B and C due. And then on Tuesday, what we're going to do for lab is we're going to have a study day. There's going to be kind of a bunch of worksheets and fun, and I don't know, I think they're fun activities. You guys may decide that they're not very much fun. But they're designed to try to see if we can either learn the material in a different way or just show our mastery of the material that we've had so far. So it'll cover things like naming and reactions, and it'll kind of stick all of chapter 19 and 20 together because that's how you need to study for the test. You can't just study chapter 19 and you can't just study chapter 20 because that's not going to work in the long run. You have to stick them together. And so that's what we're going to kind of do that day. And then on Thursday, I haven't really decided what we're going to do for sure. On Wednesday, what we'll do is we'll lecture and we'll finish up chapter 20. That stuff will be due Friday. I'm thinking next week on Tuesday we'll have an exam all over chapter 19 and 20. The other alternative is to have it on Monday, but I think it would probably be a good idea to let people have a chance to ask questions. So we'll put it in on Tuesday then. That way Brittany can have a fun weekend snow machining and stuff for her birthday, and the rest of you can have time to study. Okay, so let's take a look at aromatics. Aromatics are compounds that have one thing in common. They have at least this functional group, which is a six-membered ring with alternating carbon-carbon double bonds. And it doesn't matter how you draw that ring, meaning it doesn't matter where you show those alternating double bonds. Here I started in the upper left or upper right corner and went around, but I can just as easily do kind of going from the upper left and going around counterclockwise every other bond. Those are the exact same molecule. And in fact, what we really find out is that because of those double bonds, and because they can be in more than one place, we can actually have a resonance structure, where what it really looks like is each one of those sides kind of has a bond and a half. And so sometimes you'll see it drawn like that. And the way the computer, or the way I draw it when I'm lazy instead of drawing all the double bonds, is sometimes they'll just put a circle in the inside, saying that those double bonds really kind of form a continuous ring of electron density. And this specific molecule is given the name benzene. How many people have heard of benzene before? In what respect? Benzene is one of those compounds that's commonly known as a carcinogen. You might have seen it if you talk about DNA, because it can cause problems with that. Kind of looks like the six-membered rings in DNA when we get there, and we'll talk more detail about it then. And it's a side product of a lot of industrial processes, and it's also the starting product of a lot of industrial processes. And so benzene itself is a fairly important molecule. Now, we're not really going to deal with benzene just by itself. We're going to be, of course, adding different functional groups on it. And so there's 5 special groups that have names. And actually, maybe it's 6, I forget. So we'll just put some special groups down. And they all have that benzene ring, and then they have some functional group. So if there's just a methyl on it, that's toluene. That you should remember from the experiment that we did over the week. And depending upon the functional group, we give it a different name from benzene. Don't ask me why they do this. This is one of those mysteries to me. I would rather just call that hydroxybenzene or something silly like that, but they give it a special name. This is called phenol. And so if it's got an alcohol group on it, it's called phenol. If I throw a carboxylic acid functional group on it, meaning it's got that double bond, or that carbon that's got a double bond to oxygen and then an OH group, we call this benzoic acid. That at least makes sense. I mean, benzene, benzoic, I can kind of imagine that. If I put an aldehyde functional group on it, we're going to call this benzaldehyde. And notice that the aldehyde and the carboxylic acid functional groups are pretty close. It's just the difference between an OH and just an H on that carbon. So this is called benzaldehyde. We can add an NH2 group on it, in which case it's called aniline. Yeah, benzoic, B-E-N-Z-O-I-C. So you have to memorize each of these 5 special ones in order to name aromatics. Instead of having sort of a common system of naming for aromatics, the aromatic system is all broken up into little things. And so it depends on whether there's 1, 2, or 3 things on it. And then it depends if it's just a plain old benzene ring, or if it's got one of these functional groups on it, then it's named according to that functional group. And so the naming is not easy. It's kind of annoying. Once you pick up on the pattern, I think you'll be okay. It's just sort of a lot of memorization for all those new functional groups. Does everyone have those functional groups down? I need to get you guys caffeinated so you write faster. So we're going to have 3 sets of rules. We're going to have rules for if there's 1 thing stuck on it, 2 things stuck on it, or 3 things stuck on it. 3 or more, really. So we can talk about single substitution. In which case we name them just like normal. And so if I have something that is a benzene ring, I just have a plain chlorine on it. This is just chlorobenzene. Or if I have a benzene with just an ethyl group on it, we would call this ethylbenzene. So for one group, it's pretty much normal, except you have to remember that we have those tricky ones. It's ethylbenzene if I've got an ethyl group on it, but what if I just throw a methyl group on it? Yeah, that's just really toluene. And so you have to be careful. If I have just one thing on it, and it's one of the special ones, it's those 5 special names. And if it's one of the just regular things like chlorine, fluorine, bromine, iodine, or some other group stuck on it, then we simply call it by whatever we would normally, call that side chain. So like chlorobenzene or fluorobenzene. The other thing to recognize is, remember, it doesn't matter, especially when there's only one thing on it, where I draw that, right? Both those molecules are chlorobenzene, whether it's pointing up or pointing down, because I can always rotate those molecules in space to make that chlorine that's pointing up pointing down, or vice versa. So there's a lot of symmetry in these benzene compounds. No space. Hopefully there's no spaces the way I wrote them. Although I guess maybe it's a little tough to tell. But there are no spaces. When there's a space in a name, which we haven't encountered yet, except for, I guess technically I should point this out, benzoic acid really is 2 words. So that's the only case where we have 2 words in a name. So if we have single substitution, it's like that. If I have what's called disubstitution, they introduce a whole new set of rules based on the relationship between those atoms to each other. So if I've got 2 things on this molecule, and we're going to keep it generic, I'm just going to call them X and Y to start with. If X and Y are right next to each other, we're going to call that ortho. And if the X and the Y are 1 away from each other, say for instance I've got an X and a Y like this, we're going to call that meta. And then the third one is if they're on opposite sides of the molecule, we call that a para molecule. So we've got ortho, meta, and para depending upon where they are in relationship to each other. And if I wanted to summarize that in one picture, what I usually do is something like this. You know, if my X is here and my second group is in either of the positions next to it, that's ortho. If it's 1 away from it, that's meta. And if it's opposite of it, we call that para. So ortho, meta, para. So if do you want me to go back for a second? So the idea for these aromatic compounds is, first off, memorize the 5 special ones. Then remember whether you're naming it with 1 thing stuck on it, 2 things stuck on it, or 3 or more things stuck on it. And the ones that are the tough ones are remembering the 5 special names and then remembering the ortho, meta, para, because the rest of them kind of default to what we would expect normally. So for instance, if I draw a molecule like this with a chlorine and a chlorine, is this ortho, meta, or para? Meta. So this is going to be meta dichlorobenzene. Or sometimes they'll abbreviate it M dichlorobenzene. And I guess to be careful, I should put the dash in there for meta. And so sometimes they write the word meta out. I'm lazy. Oops, dichloro has an O in there. We should make sure that we have that. And see, I can draw that molecule also in a lot of different ways, right? Meaning, don't get stuck in that it always has to be up. What if it's like this? Same thing, right? Or, you know, I can draw a whole series of molecules where, you know, they look maybe different, but they're all the same molecule. So I drew 4 molecules there, but they're all the same, right? They all have the chlorines 1 away from each other, meaning there's a space in between them. And we can go like this. If I have 2 different groups, for instance, say I have a bromine and a fluorine. First off, ortho, meta, or para? Para. So we're going to call this P. And then should I name the bromine or the fluorine first? Yeah, bromo, fluoro, benzene. And again, I can draw that all sorts of different ways, but it's always going to be directly across from each other. So it's always going to be P, bromo, fluoro, benzene.
So you don't say para in your answer?
You can write the word para if you want. I'm not going to mark you wrong. The computer, I think, only accepts just one answer for this one, although I might go back and fix the computer so it accepts either at some point. But for now, I'm lazy, so I just call it p-bromofluorobenzene.
There's no more writing of a user.
Well, the P is what you're going to see more often instead of para. Now, where you have to start getting tricky ortho, meta, or para? Meta, because it's one apart, right? So this is M-bromo. And then we have to remember that it's not, since we don't really know what this functional group is anyway, I guess it's not horrible to say we can't really name it following our normal rules. But that's M-bromobenzoic acid. And there really is a space there between benzoic and acid. And so we have to remember those 5 special names, because if one of them is on there, it changes our ending from benzene to something else. What's that? Ortho, ethyl, right? And phenol. Be careful. I'm going to overpronounce that phenol because we're going to learn that there's also something called phenyl with a YL at the end of it, because organic chemistry isn't confusing enough. They have to make one letter make a difference. So ortho ethyl phenol or O-ethyl phenol. And see, it kind of gets silly because this kind of looks like it should be dimethyl, right? Well, what do we have to remember? If it's got one of them, it's really toluene, and so this is M-methyl toluene. And to get even worse, it's actually possible that people would just call that by another name called xylene. But we're not going to worry about that. Meaning, aromatic chemistry is kind of goofy and screwed up, so we'll try to stay and keep it reasonably easy. So that's if I have 2 things, I have to use ortho, meta, and para. And then if I have 3 things, 3 or more, we number like normal. But we also have to remember to give any special groups the lowest number. So for instance, if I have something like this, we're actually going to number it. And so where should I start numbering? Yeah, this should be 1, 2, 3. And so this should be 1 bromo dash 3 chloro dash 2 iodo benzene. Where remember, we number to give the lowest set of numbers. If there's a tie, we go alphabetical. But then when we number anything, it's always alphabetical. What would I name this? Or actually, I suppose, where should I start numbering it? Yeah, since this is one of the special ones, that's got to be our 1. And then in this case, it doesn't matter. I made it nice and symmetrical which way we go. And so this is 3, 5 dichloro benzaldehyde. Now, why don't I need a 1 in there? So the 1 is redundant. because by automatically saying I have benzaldehyde, that automatically puts it at the number 1 position. Well, see, they're not really meta. They're meta to each other, right? And technically they're meta to that benzoic acid, but since there's 3 groups on here, we're going to use numbers. So if there's 2 things stuck to it, OMP, 3 things or more, numbers. And if it's only 1 thing, you don't need any numbers, obviously, because that would be redundant. So, making sense? Yes, no? Again, best way is practice. Practice really, I think, is about, you know, that saying practice makes perfect. Sometimes I think it's silly and that practice doesn't necessarily make you any better at something. But in this case, it's the only way to get better at it, I think. It's the only way to tell if you really know it. I can't imagine taking this test without having done the homework. It would be mind-boggling. Okay, one last example, just because it's a fun one. Now, you don't know what an NO2 group is, but we'll tell you. So NO2 is just nitro. So where would we start numbering first off? Yeah, so 1, 2, 3, 4, 5, 6. And so what should we call this? We've got nitro groups on 2, 4, and 6. There's 3 of them, so trinitro, and then toluene.
You don't do anything with the methyl?
Well, remember, that's the toluene part. And so a methyl is usually a methyl unless it's on a benzene ring, in which case it's a toluene. Like I said, the rules make no sense. They're pretty, to me, arbitrary. Now, what do you think people normally call that? Yep, TNT, trinitrotoluene. So no one ever calls it trinitrotoluene very often. They call it TNT. That's also the sad part about organic compounds is 9 times out of 10, if it's any bigger than a simple, like, quick name, people just make up some other name to call it by, either a trademark or a brand name or something like that, to keep it kind of easier. One last thing we have to take a look at for these is that sometimes this is a side chain, in which case we call this phenyl, like a side chain normally has the YL ending. So you have to be really careful. Phenol, OL, phenyl, YL. And so, like I said, a lot of times I overpronounce it trying to make sure that we keep it or get it right. And we're going to know that it's a side chain when we can't name it like a normal compound. So even though it might be drawn, especially since phenol groups are usually pretty large, we wouldn't know how to name that if we tried to name that as a benzene, right? Because if we named it as a benzene, we have a side chain here, right? But then notice I've got a side chain on my side chain. So instead what we're saying is where I drew the dots, that's my main chain. Because I don't know how to name that as a side chain on a benzene atom. Even though we kind of could probably figure out how to do it if we really wanted to. For examples like this, if you can't name that side chain on a benzene ring, then the benzene ring is the side chain. So where should I start numbering on this? Nope, the left. Because the benzene ring is then on the number 1 carbon, right? We want to have the lowest possible numbers. And so this is 3-methyl dash 1-phenyl butane. So if you can't name the side chain, if it's got a side chain kind of on a side chain, then you have to say that the benzene ring isn't the main part of the molecule anymore, it's just a side chain. And it's tough because, you know, that and this, in this case, we can name this, right? Because we can say, oh, 4 carbons, this is just, oops, not propyl, but butyl benzene. And so, you know, in one case it's a side chain, and in the other case it's the main part of the molecule. The nice thing is if there's a phenyl group on the molecule 9 times out of 10, it's the spot where you start counting as 1, since it has to be on the kind of the end of the molecule usually. You can have weird things like this. And it doesn't have to be in the middle. Here, we'll make this fun. So in this case, if you think about it as the benzene being the main part of the molecule, there's no way you could possibly name that side chain, could you? Because it's got a chlorine, a bromine, and a double bond in it. So instead, what we're going to assume is that the benzene ring is a side chain. So which side do I start numbering at, left or right? Yeah, because I have to give that carbon-carbon double bond the smallest group. And then I got to look hard. This is going to be ugly. Let's see. We got a bromine comes first, so we've got a 6 bromo, and then a 5 chloro, and then a 3 phenyl, and then it's 1 hexene with an E-N-E ending. So sometimes that benzene ring is really a side chain, just to make life, I don't know, fun, entertaining, different. We have those all be silly. Okay, so let's take a look at reactions with benzene rings, or aromatics, I guess, really, we usually say it that way. So, aromatics are unique. Aromatics. How am I? Oh, I'm skipping. I'm like skipping the O, trying to figure out. In that those alternating carbon-carbon double bonds are extremely stable. And there are other compounds that are not benzene rings that have these alternating carbon-carbon double bonds that are also stable molecules. We won't worry about those and differentiate those from molecules that just have more than one carbon-carbon double bond, because it's really not that useful and not that common. But what we find is that since aromatics have those alternating double bonds, that these tend to react like alkanes. In that they're fairly non-reactive, and they tend to react via substitution or elimination, not by addition across those carbon-carbon double bonds. So if you see a benzene ring in a molecule, that benzene ring doesn't change. It's very stable. Yeah, that's an ANES. So even though we see those double bonds there, it ends up that we ignore them and we treat them just like alkanes. So arguably, we're not going to learn anything new here. We're just going to apply what we already know to kind of a new class of molecules. So for example, we can have substitution reactions, where if we take our benzene ring plus, say, X2, we keep our benzene ring, and we realize that there's just a swapping between that H and an X. And so I end up with a benzene with, say, an X on it and HX, or an acid. And so that's just like the alkanes. And then in this case, we only get one product because all of the positions are the same on that molecule, right? meaning one hydrogen is all the hydrogens on that molecule are the same. Now if I do something silly, just to make it more complicated, and say throw a methyl group on there, now all the positions aren't equal, and say we throw some chlorine on there, I can have a bunch of different products now, right? So which hydrogens on that molecule can react? Well, I've got a hydrogen on the end of the methyl group that can react, right? I've got hydrogens one away from the methyl group that can react, but notice that the other one on this side is just a duplicate, so I won't allow that one to react, right? I can react two away, but again, on the other side, that's just the same one, right? And then I've got the one facing down. And so I've got 4 different hydrogens on this molecule that can react. And so I can get something that looks like this. And I can draw 4 more. And I'm getting lazy. I'm going to stop drawing the double bonds and just put a circle because, well, like I said, I'm lazy and it's a lot easier. And so I get the same molecule and I can put a chlorine here, or a chlorine here, or a chlorine on the opposite side, and of course, plus HCl. And there are rules for stability for these, whether the ortho, the meta, and the para position are more stable, but it also depends on the substituent on it. And so for benzenes, we're going to make, I don't know if I'd say it's an exception to the rule, but we're not going to worry about which one of those is the most stable, simply because it's a pain in the butt, and it's just one more thing that we don't need to worry about. And of course, I can react anything on there that I want, right? Meaning it doesn't have to be X2. What else could I react? Well, I could react what? Well, yeah, bromine instead of chlorine, but I'm saying something that's different than those, because those are all halogens, right? I can also react acids, like if I react HCl, then again, I'm going to get the same product for the organic part, but now I'm going to get hydrogen gas. Or what else can I react for substitution reactions? What are other things that we've substituted in? Yeah, water, in which case I get phenol actually, plus hydrogen gas. And what's the last miscellaneous thing that we reacted to these? There's always, I can react an acid, a halide, an alkyl halide, water. Is there anything else? Not really. I mean, there are other things. We can actually react what's called nitric acid, HNO3, and that breaks apart by doing an NO2 plus an OH, and so what you end up getting is a nitrobenzene plus water. So that's how you start making trinitrotoluene, or TNT. You basically take toluene and start reacting it with nitric acid, and you make TNT eventually. It's a little more complicated than that because you want to make sure the NO2 groups are in the right spot in that molecule, but you know, the basic idea is there. So normal substitution reaction, we don't break any carbon-carbon double bonds on the molecule, okay? Now there are some unique reactions with aromatics. The first one is called an alkylation. And it really is just a substitution. But instead of substituting something that is a small molecule, we substitute an actual alkyl group. So if I have something that looks like a benzene ring plus, say, chlorobutane, then when I do the swapping, I've got kind of 2 choices of what to swap. But in this case, I almost always swap the butane, or the butane part, and get HCl. So really we should get 2 products, meaning I should have some of that, and I should have some where I just have a chlorine and then the butane, but this one is so heavily favored that essentially we don't bother drawing the second product. And so in this case, we would just draw that singular product where we swap a chlorine and a hydrogen. And it's called an alkylation because that butane group, that's called an alkyl group if it's, you know, just normal carbon type stuff. And on the arrow, quite often, you'll see sometimes things like AlCl3 written or something else. I don't think that's terribly useful, but it is required for the reaction to occur, meaning that might be something you can train your brain into going and saying, oh, that's an alkylation because it's got AlCl3. Or really, if you think about it, it's just a special case of a substitution in which we only make a single product instead of the double products. Well, yeah, that's what I'm saying. You really get two products, right? But the second set of products that you get doesn't happen, and so we'll only write this first part. But really, if you think about it as substitution, you should get double sets, right? You should be able to do two different swaps in this case. Just the one. That's why I say it's kind of an exception to the rule. We'll just draw the singular product. The other one that's unique for aromatics is called side chain oxidation. And what happens here is if we take our normal benzene group and we've got an R group here and we're going to oxidize it. So we usually use that oxygen arrow with the O across it. Sometimes you'll see it as KMnO4, meaning that's a standard oxidizing reagent that we know about. But in this case, what I'm going to do is when I draw it on the tests and on the quizzes and stuff, it'll just be that oxidation arrow. But I want you to realize that it could be any of the other oxidation arrows that we've talked about, meaning they all do the same thing. And what it turns our compound into is benzoic acid plus a second carboxylic acid that's short one carbon. So that R-1 means it's short a carbon, right? See, R stands for any group, right? So for instance, if this had 4 carbons, then this means this part only has 3 carbons. I'll draw a real example in a second. This is generic, right? The way I like to think about the reaction is that if you've got a side chain, what the oxidation does is it always breaks it between the first and the second carbon. And so that when I oxidize it, I get that carbon with a double bond to oxygen. So there's that carbon right there. So here's the number 1 carbon. And then I get another carbon chain. In this case, it's only 4 carbons long. And it's got that carboxylic acid functional group on it too. 1, 2, 3, 4. And so notice that 1, 2, 3, this was 5 carbons to start with. And this is only 4 carbons when we end it. So we leave 1 carbon behind on that benzene ring. Well, the dot represents where a carbon is, right, in the Lewis structure. Now, the computer doesn't draw the dot. The computer just draws it like this. And you're supposed to realize that in order to make a Lewis structure, there has to be a carbon there. Me, I tend to either draw it as a, just a line with a dot. Sometimes I'll put the carbon in there. I am a little sloppy on that part, but the computer itself will just draw a line there. And you have to realize that obviously there has to be a carbon there because you can't have an oxygen double bonded and an oxygen single bonded and all that stuff to just nothing. That's extra, remember, that's not part of the reaction. And so notice it does follow our normal rules of oxidation in that we gain bonds to oxygen. That's a classic sign that an oxidation has occurred. And there's one exception to this rule. if my benzene, and this is the only time you'll ever see it, so I don't know why I bother showing it, other than, gosh knows if I'm not careful, I'll put it on a test accidentally. If I've only got one carbon there, then we automatically just get benzene plus CO2 gas. So if there's only a single carbon on the side chain, it's automatically just broken off entirely into carbon dioxide, and we're left with a benzene ring. And the only reason I show that is if you read the book, you'll see that, and you'll be like, well, wait, why didn't it form a carboxylic acid there? Well, this is the exception to the rule. One of the reasons I think chemistry is so hard is that the rules are really difficult. And so when we generally make rules, we have to make a rule and then say that there's exceptions to the rule instead of making a really hard rule that would, explain everything. And so we tend to make a simple rule with exceptions rather than a very complicated rule that no one would be able to understand. So that is the reactions of aromatics. So the key is to remember that aromatics really react like alkanes, meaning that on the Chapter 20 homework, you're going to have mostly addition reactions, right? But every time you see a benzene ring, you should be suspecting that there might be a substitution. Now, if they're mixed together, what should we expect to happen? So if I have something like this, what should I expect to have happen? Because I've got both a benzene and a double bond, right? Yeah, remember we said that these are the most reactive. So really what we should expect is an addition reaction in which we simply add a chlorine to both sides of the double bond. So we should treat it like an addition. That being said, if you really did this reaction, would you get a few cases where the double bond maybe didn't react and there's a chlorine stuck on the benzene ring? Yeah. One of the things about alkane chemistry is it's really ugly in that when you really do a substitution reaction, you can't just make it only be monosubstitution. That you're going to get a big mixture of products where the majority of them are monosubstitution because the reaction happens fairly quickly, but some molecules might have 2 or 3 or 4 chlorines on them. And so, in general, when people do reactions with alkanes, the very first thing they do is turn it into something else so that they can control where the reaction occurs. But that's alkanes in a nutshell. Okay, we have one last miscellaneous set of topics to talk about for this. And where is my miscellaneous set of notes? And actually, it's one of those things that we could actually save for another day, because I got to be honest, alkanes, alkenes, and alkynes aren't terribly exciting as a set or a class of molecules. But we got no time left technically, because when am I supposed to end this class? Let me think. 8:45. 8:35, yeah, let's just end for once at a normal time. And I won't push it. And what we'll do is we'll cover that topic on Wednesday. And then on Wednesday, we're also going to have to start in on the next chapter. So the way that this first test is going to happen, we're going to have a good chunk of Chapter 22 already done also, which sometimes I feel bad about, but I really want you to also have a lot of time to study. So I don't know, maybe we should have the test on Monday and just have a study session Sunday night. I don't know. We'll have to think about this hard.